Hello, also from MongoDB side, and myself. My name is Rafael Shore, and I'm a principal for manufacturing in motion at MongoDB. My talk today is about leveraging the power of vector search for root cause diagnostics. So my agenda is pretty short, as my task is. So in the next 20 to 25 minutes, I'm basically going to talk about three things. I'll start with the challenges on root cause diagnostic. Why is it so difficult? But why would it also be very useful to have it? And then I do a pretty hard cut to the whole vector topic. So what is a vector? What's vectorization? What is it used for? And I'll try to bring these two things together and create an architecture for a root cause analytics, also by using some AWS services. But for those who are not familiar with MongoDB yet, let me use a couple of minutes to introduce MongoDB. Since its founding 2007, MongoDB is not a startup anymore. We have more than 365 million downloads of our database and more than 45,000 customers all over the world. Since years, MongoDB is voted as the most wanted database by developers and named the leader in Gartner's Magic Quadrant for cloud database management systems. Since 2007, MongoDB developed also from a database to a whole developer data platform. At its core is still the database with its very, very flexible document model in a JSON-like schema. So MongoDB is a non-relational database. It is very flexible and allows developers to use all kinds of data in one data set. Let it be time series, let it be graph, geospatial data, whatever. So no matter what data you have, you can store it right in your single one document. It's really made in a way developers think and code. Usually I hear that non-relational databases are not ACID compliant, but MongoDB is. Just as an example, 12 out of the 15 biggest banks of the world run their financial transaction systems on MongoDB. I think that speaks for its own. MongoDB is also high available. We have our replica sets, so all the data you store in MongoDB Atlas are stored in at least 3 nodes. Where do you want to deploy these nodes is up to you. Also there you have a high flexibility how you want to deploy that. One of our latest features are dedicated search nodes. So you can have your operational or transactional data doing all the reads and writes from the daily transaction, and besides you have a real-time copy just for your analytics. Since 7 or 8 months now, we have also included vector and vector search. This enables all these Gen AI applications combined with any kind of large language models. MongoDB is built to run everywhere, started on the mobile applications. With our very little database called MongoDB Realm, or now Device SDK, you can run mobile applications literally on every device that is capable to connect with the cloud. For edge computing, we have Atlas Edge Server. So on a factory shop floor, you can collect all your data from your production line or whatever, bringing it to the edge server, and from there, connecting to the cloud. And the edge server is capable to already do some pre-processing of your data. Of course, there is also an on-prem solution available for MongoDB called MongoDB EA. But our main feature product, what I'm talking about today as well, is MongoDB Atlas. MongoDB Atlas is very well fitted into the whole ecosystem of AWS. It's integrated in the marketplace, and we have a very deep collaboration together with AWS. As an example here, for those of you who know Amazon Code Whisperer is trained to the MongoDB query language. So also that's a perfect fit. Of course, MongoDB is also multi-cloud. You can run basically on every cloud you would like to. And none of these functions would matter the slightest if we didn't focus on the fundamentals of resilience, scaling, and security at a very deep level of the architecture. So in short, MongoDB is a powerful data platform allowing you to combine various data sets easily through its flexible data model, at scale, of course. It maximizes your developer productivity and helps you to build more faster. When looking through the manufacturing lens or the industry lens, MongoDB is spread all across the value chain. Our clients use us for smart supply chain applications in the smart factory, smart commerce, smart products, literally everywhere. Here you see some customer use cases. They are all public. You can find all of them on our homepage. Today, I'm only going to talk about root cause analysis and not about the use cases on top. But if you would like to know more about these use cases, I'm more than happy to answer these questions at the booth right behind me. So now let us jump into the actual topic, root cause analysis, and what I understand under that, and why should we do all that. So in the context of manufacturing, root cause diagnostics is a crucial tool for solving problems, for improving processes, and also for boosting the overall productivity and quality. So root cause analytics is much more than just putting out fires. What we basically do with our, I call it the traditional machine learning methods. It's about going beyond the symptoms to identify the underlying root cause of issues so we can fix them permanently and prevent them from reoccurring. In other words, root cause diagnostics eliminates recurring problems by addressing the true root cause, avoiding temporary fixes, and prevents the same issues from popping up again and again and again. This saves a lot of time, money, and resources. Root cause analysis or diagnostics can also enhance process efficiencies by identifying bottlenecks and inefficiencies at their core, leading to increased output and lower production costs. And of course, it also drives your continuous improvement, right? The systematic approach of root cause diagnostics fosters a culture of learning and problem solving, encouraging ongoing process improvements and innovation. But to reach that is not easy at all. So root cause diagnostics in the manufacturing environment is often very, very challenging. Manufacturing processes generate vast amounts of highly complex and sometimes also noisy data from all kinds of machines, sensors, and other sources, make it very, very challenging to identify root cause of issues. So machine diagnostics often require the integration also of diverse data types as well as from siloed data. On today's traditional ways, it needs a lot of human expertise, knowledge, and experience to do any root cause analysis. How can we solve that problem? We can bring Gen AI into the play. So utilizing Gen AI can significantly enhance your root cause diagnostics by offering several key advantages. It ensures scientific objectivity because Gen AI is trained on a vast amount of scientific data and principles. It allows you to analyze potential root causes with objective and an unbiased lens. So Gen AI can scan through evidence, identify correlations without being influenced by personal experience or emotions. It also enables very much your hypothesis testing, right? If you have a Gen AI kind of a chatbot or so, you can create a hypothesis, you can prompt it, and you get immediately your scenario back. And it has also another feature. Imagine you have on every root cause analysis session or on every whiteboard session your industry-specific expert with you. Gen AI can be used to take exactly that role. you can ask it, or you can use it to take place as a senior operator, as a field or a material scientist or a process engineer. And it gives you exact the information back out of that perspective. But please remember, Gen AI is not able to replace humans at all, but it's here to augment it. Now let me do that hard cut I announced to my second chapter about the vectors and vector search. For those who are not yet familiar anymore what a vector is, I'm sure all of you learned that in school, I quickly recap that. So in math terms, it's just a data structure. In developer terms, it's an array. We store a list of points that make up a representation of an information in multidimensional spaces. So here, unfortunately, I'm just able to show you 2 dimensions, but there are many more possible. And based on that points, we can calculate the similarity between the terms, right? So if you see here, cheese and mozzarella have the same distance, or cheddar and mozzarella have the same distance to cheese, but pizza is closer to mozzarella than to cheddar. That's why mozzarella is the most often used cheese for pizza. And so that's the mechanism how we can create the context that we need. So that's also what we get more than by searching for simple texts. But why is that now such a topic? And a little fun fact here, I'm a bit struggling with the clicker. It's not new at all, right? We know how to calculate the closest distance or the Euclidean distance since 300 BC. We know the cosine product and dot product since 1881. And the most used algorithm, the KNN algorithm, is available since 1951. What's new and why everybody is talking about that are the transformers, or basically LLMs, in other words, who enable calculating a lot more data powered by the very strong CPUs available today. Having said this, the devil is still in the detail of how we convert words, terms, or phrases into a vector. Let me do another quick example here just to clarify how Gen AI actually works for those who are not familiar with that. So I have questions. I want to know what salami is. So I take a large language model, prompt that sentence is. The large language model calculates me a vector and embeds that into my database. The vector search now searches for the closest data available to that vector you generated. And it creates a new vector and gives that back to the LLM, and that then transforms that to an answer in a natural language. So if I ask here my example, what is salami? I most probably get the answer that salami is a beverage often combined with mozzarella cheese on a pizza. Way more likely that I get the answer that salami is a beverage served with coffee and tea. So we can take the data from any unstructured information into multidimensional vector. And again, that is exactly what creates a context of meaning and differentiates from a traditional text search. Up to now, I only talked about information or text or so. But the cool thing on the vectorization is that we can use literally all the information available and transform it to a vector. Let it be an audio file, let it be a PowerPoint presentation, let it even be your hand notes as long as they are OCR readable, so maybe not my hand notes. It can also be PDFs, and you even can extract the information of graphics out of a PDF, vectorize that, put it into a LLM, like here Amazon Bedrock, and then store that information in a vector database. And that's the place where MongoDB comes into the play. MongoDB Vector Atlas has included vector storage and vector search capabilities, And if you store your vectors there, you also get fully automated indexing, and you don't have to care about that. WaterWix is much faster. MongoDB Atlas is able to calculate the closest vectors and give you back the result of it within milliseconds. At the very beginning, I talked about the document model, the differentiation to a relational database. Here you can see how a document model looks like, and it's exactly like that. You have on top your metadata or your structured data started by a unique document ID. Then you have some structured data, and right in that same document, you're able to store all your vectors. Today, we are able to store up to 4,096 dimensions in one single document of the vectors. That's, as far as I know, also the maximum what the LLMs can handle. As already said, with MongoDB Atlas, there's no need for a dedicated vector database, no different APIs, no ETL processes, no maintenance effort. You get all out of one database. Let me now connect these two things together that I was talking about. So we have the root cause analysis, where we want to know why something happened. Here in the example, I want to know why my tool braked. And I would like to get an answer that my tool braked on during job whatever, 001 here, and the cause was most probably high vibrations, elevated temperature, and misalignment of the tool. For traditional machine learning models, I only use the structured data. Combined, traditional machine learning models together with all the unstructured data delivered by the vectorization and GenAI, I can enhance my data set, and I can create way more satisfying answers. But how do we realize that? All starts with a very traditional data collection that you know since years from the shop floor. So you have your operational data, you have your MES data, you have your very structured data from sensors. Ideally, you use an MQTT broker because the MQTT format perfectly fits because it's also JSON-like into the document model. And by the way, here, just as a side effect, we also highly recommend the concept of the unified namespace, if you ever heard about that. Also using the ISA 95 history, where your data structure starts with the factory, then you have the shop floor, then you have the machine, and you go down to the one single sensor. You can perfectly build that structure into a JSON document and also query the data exactly that way. So this is also how we store the data in MQTT format. With that, I can predict my remaining lifetime. So, like with a traditional machine learning model, I can use the included aggregation framework here to summarize and process data. I can use the trigger functions for thresholds or also to trigger my machine learning model. I can use something here like Amazon SageMaker. Up to this point, we are in the very traditional predictive maintenance based on statistics and sensor data. That's, as I said, what we already know and what some of us are doing since many, many years. We can train these machine learning models to get valuable insights and prediction of failures or the remaining lifetime. But in a case something breaks, we still don't know why that happened. And here is where GenAI comes into play. As an example, GenAI can help me to analyze also historical data to identify patterns and correlations that may not be apparent to humans, operators, and relies not only on structured data. We can enrich our MongoDB Atlas database with additional information from all these data. So as an example, we also could continuously record the sound of a machine, vectorize that data, and use that data. Something we couldn't measure with electronic sensors or something like that. We can also save manuals, meeting notes from previous claims, and use that data. or the information where past breakdowns were discussed. All this is valid data to consider. To do this, we need an embedding creator, such as Amazon Bedrock, what we used here, which processes all this information into vectors. All these vectors are stored right next to the same data set as your structured data. That makes it very, very easy to query and to make useful data out of it. Having that structure then already is a small step. So with the help of Amazon Lex as a chatbot application, we can now very easily create a chatbot that converts our requests in natural language into vectors and send them back to Atlas. A vector search is then used to calculate an answer, which in turn sends it back to Bedrock, where it's again with the same principle converted to your answer in a natural text. So root cause analysis is not machine learning or Gen AI. It's the combination of both of the systems that will facilitate that. And it's all based on a very small tech stack, as you've seen. So we only use a handful of technologies. We use an MQTT broker, we use MongoDB Atlas, we use Amazon Bedrock, Amazon SageMaker, and Amazon Lex. And that's it. And with that small tech stack, you can run applications like these ones. So if you now got curious how that real works in production or on a demo, we have something very, very similar, not exactly that one, running on our demo, on our booth. So you're invited to show up there, and we can show you how that exactly works. We also have a white paper available about many other Gen AI use cases built on MongoDB, free to download. You can find it when you scan the QR code here, as we also have many, many other very useful information on our homepage. And with that, I'm at the end of my talk. Thank you for listening, and I think we have a few minutes for questions, if there are any.
Tess, have you found better vectorizations coming from different databases, like a graph database versus just a standard relational?
You know, the vectorization itself is coming from the large language model, and there we have huge differences, right? Every day or every week we see new large language models popping up, and one is better on that use case, one is better on that use case. So it way more depends on the large language model that you use, on the model behind, than on the database.
Gotcha, thank you.
Other questions? If not, thank you very much for listening, and I'm happy to see some of you at our booth. Thank you.